Hi everyone, I am Roshni. We the team members from the Hyderabad Institute of Technology and Management, and we are giving the challenge for the Simulink Students Challenge for the 2022 with the title of PV Self-Fed Synchronous SEPIC Closed Loop Converter for BLDC motor drive applications. So this is a block diagram for these BLDC motor drive applications. So generally, by using the BLDC nothing but it will completely based on the DC motors. So DC supply. So here from photovoltaic generator, I mean PV cell. Here we are generating the DC voltage. From that DC voltage will be given to the SEPIC converter, and SEPIC converter will be given to the BLDC motor drive applications. So in the main aim is the applications which you are getting in the BLDC, which will be controlled by the SEPIC converter, and that SEPIC converter will be controlled by the PWM converter control. So this is a basic block diagram of the open loop SEPIC converter. Here SEPIC nothing but single-ended primary inductance conductor. So SEPIC nothing but it is one word. It can be redefined as a buck boost converter, so we can reduce the, I mean we can buck or boost the voltage as per our requirement. So here in this open loop SEPI converter, first we will given the DC supply from the PV cell. That DC supply will be given to this SEPIC, and the through this SEPIC the output will be given here. But here in this, through this open loop SEPIC converter, here we'll get an output like this. See here we'll get in so many distortions due to the open loop conditions, because we are getting the output. It's not an pure one, like it's reduced or minimity buck or boost, but it's not completely effective one. So that's why to get an effective output, we are going for the closed loop synchronous SEPIC. So this is a complete closed loop one. So as it we are considering as a closed loop one, so it is also as named as synchronous SEPIC. So why it is called synchronous SEPIC? Nothing but the concept will be same. SEPIC will be step down the voltage depending upon requirement, but the output will be controlled by this PWM controller. See here from the output we are taking as an uh, uh, constant value. So that constant value will be compared with an integrator, and that after that integrator we will comparing, or will creating an we are comparing with another value. So due to that value we'll get a constant output, and that constant output will be given to the MOSFET. So this MOSFET will be rectified as per our requirement voltage, that will be given to the second MOSFET. So it's completely like if suppose in a synchronous, I mean as a sine wave, if we are giving the sine wave by using the PWM, so depending upon requirement only, it will chop that converter. Like so, as it is a DC to DC converter, it will chop the voltage and will get a constant output voltage. So by this, we will get an output like this. See the distortions which we got in the previous open loop, that will be completely reduced in this open loop SEPIC converter. So basically, this open loop SEPIC converter will be applied for the one real-time application, that is a BLDC motor. See, this is a BLDC motor. In this, the same concept closed loop synchronous epic will be completely applied to the BLDC motor drives. So here, as we know, BLDC motor nothing but will have in two types of waves. One is a trapezoidal as well as a sine wave. So, as per our convenient, we can use trapezoidal as well as a sinusoidal. Here, I'm using trapezoidal. So, here from the constant voltage 1500 volts, we have in subsystems here. I will go through that one. So from the subsystem, so from the speed regulator PI, it's a integrator that will be given to the gain, and that will be given to the output. See, this is a gate pulses. This is a completely gate pulses. So from everything will coming will get an gate pulses that will be compared, and that every each and every output of one subsystem will be given to the input of another system. See here, one and two, this will be the positive ones that will be given to the inverter. Here if we are using the sinusoidal wave, will given, it will be converted to the for inverters like, see here, A, B, C, D, three phases. That three phases will be again given to the BLDC motor, and that BLDC motor, from the BLDC will have in these four applications. One is EMF, one is stator current, back EMF, rotor speed, and electromagnetic torque. So these come to drive these complete applications. We are using these subsystems. See, this is a subsystem for gate pulse. So from the reference we are taking the one, and after that we are comparing, like from the one application we are getting one pulse, so that will be compared with another one. So like that, from the output side we are getting the three pulses. From each and every one we will compare with reference one. After getting three references, again we are taking the three different types of outputs. So those matched will be compared, and that will be given as in one gate pulse. So that gate pulse will be, see, this is a gate pulse reference, right? So this is a gate pulse. Okay. So like that, we will use this one. At the same time, here we'll use Hall effect sensors as, so this is a subsystem of the Hall effect sensors. So depending upon the gate pulse and the Hall effect sensor, we will drive the BLDC motor. So this is a motor torque. This is a speed waveform, and this is a torque. This is a current, and this is a electromagnetic torque and speed. So it is a stator current and the electromotive force. So by using synchronous SEPIC DC to DC converter, we get the constant DC output voltage, and that will be input to the DC motor through inverter. So from BLDC motor, we get the constant speed or characteristics, and also constant stator current and electromotive force with respect to the time by using the closed loop system. Thank you.